Okay, so if you're at the festival today or you have to watch this video from home, we're going to continue on with Doppler equation. And so if you were here yesterday, you would have seen me sort of go through this one, but I think we only went through one problem yesterday, correct? So I sort of ran out of time. I really like the musical display that we had brought in. We spent some decent time on that, and so I appreciate you doing that. Make sure you don't use that pencil all at once, right? So, say that. The most difficult part here is knowing whether or not to use the top or the bottom sign, and so it just takes practice. How many different scenarios can we solve with this Doppler shift equation? 4. You can handle the detector moving toward, moving away. Well, actually, technically, you could say 6. You could handle the detector moving toward, moving away, or what? Not moving at all. You could handle the source moving toward or away or not moving at all. So really you could handle like 6 different scenarios. And so what you do is you have to make sure you're choosing the appropriate sign to make sure that the mathematics work out. So I think yesterday I talked about the 2500 hertz as being the frequency that excites and gets people interested in ice cream. There is some research based on that, and I did chat GPT it last night, but I won't do that anymore if it does use a lot of, what'd you say, uses water? Okay, so I won't do that just for, I was experimenting with it some, but I won't do that if it's, unless I really need to dig into something. But what frequency does Billy hear the horn if the truck is stationary and Billy is running? So Billy must be like a near Olympic athlete, right? Because 8 meters per second is pretty good. Billy must really like ice cream. I want to know the frequency at which he hears that. So again, folks, I would suggest that you draw a little picture. As a matter of fact, if you submit a problem for consideration for the test, pictures are usually very good to include for creative measures. So maybe perhaps do that. You'll see that as a Google form request. All right, so Billy is running. He's the detector, and he's running this way. Velocity of the detector, 8 meters per second. The ice cream truck is off to the side, blaring some sound, monotone frequency here. Would you guys agree that the wave crests would look the same front and back if the ice cream truck is stationary? Do you guys agree? Sound spreads out equally in all directions. The source is not moving. So you might look at that and say, boy, it doesn't look like the wavelength in the detector's area is different than it is on the other side, but he's moving, right? So even if the source is not moving, he's going to be running into those plane waves, if you will, at a higher frequency than if he was at rest. So he was going to hear a higher frequency, even if he's the one that's moving and the other one's not. So when I go to do this, F prime would be equal to the frequency that's being emitted. That's our 2500 hertz. The ratio involves the ratio of speeds. So if there's no temperature given, we go 343 meters per second. The denominator is going to be 343 meters per second. In this case, I have the source at rest. So the denominator is not going to have anything there. The numerator, though, I have to decide what sign to use. Again, if the detector is moving toward the source, we use the top sign. The top sign up there is positive. So I would add 8 to that. And when I'm all done, I see that this value here is a dimensionless value. It's a factor. In this case, that factor is bigger than 1, which means we have a Doppler shift that's increased frequency. If you have a calculator, you could shout that out for me. That'd be wonderful. Looks like 351 over 343. 2558 hertz? Yeah. Okay, so he's going to hear a higher frequency than what's being emitted because of the Doppler shift. I want to do a couple other problems with you, and you'll see that all of these things are essentially the same kind of thing. You just have to try to figure out which way things are moving. So now here's Billy traveling west on his bicycle. So he's able to travel faster on his bicycle. Normally that would mean a higher shift because the speed is increased. The ice cream truck is moving east at 17 meters per second. Now the first part is they're approaching each other. So they're going like this. Do you guys agree that as they come together, he's going to hear a higher pitch than if they were at rest? What's going to happen when they pass? What's going to happen to that pitch that he hears as they pass? Because they're going to pass each other. What should happen? It's going to go from a high frequency, higher because they're coming together, and then as they pass, it immediately drops to a lower frequency. And so a lot of people confuse the sound level with the Doppler shift. The sound level is going to increase and then decrease as they come closer and then pass. But it's not how loud it appears that's a Doppler shift. It's the frequency. So as they come together or coming closer, as they're approaching, the frequency should be high. And then as soon as they pass, the frequency should drop. What we want to do is determine what is the change in frequency there. So we have, again, I have Billy that's traveling west here on the same roadway, if you will, as the ice cream truck is traveling east. So Billy's traveling faster or slower, so 12 meters per second. The truck is traveling at 17 meters per second. Sorry, they're not on a collision course here. They're on the side of the road and stuff like that. So, okay, we want to determine the frequency that it hears. Still emitting 2,500. Now, for this one here, we have both objects moving, so I'm gonna be a little bit more verbose in my solution. Plus or minus 12. Minus or plus 17. And I'm gonna highlight the sign that I'm using here while they're approaching. I'm not gonna add or subtract, or add and subtract. I'm gonna just do one or the other. As they're coming toward each other, would you guys agree that the detector is moving towards the source? That means I use the top sign. So when I'm going through to determine what sign I use, I'm going to use the top sign for the detector. Now, is the source going toward the detector? Yes, I use the top sign for that. So when I go through to select the signs that I'm using, I have to consider both source and detector. I notice I'm adding something to the numerator and subtracting something from the denominator. That should make that number much bigger than 1, which should happen because they're both coming towards each other. Do the math there really quick. Plug those things in. Shout that out for me. I'm not going to write it up here, just the answer I'll write. So once you have it, just shout it out. 2,722. 2722? Okay. Now I'm going to circle that one. That's the frequency that Billy hears as he's approaching the truck. Now they pass. Billy's over on this side. The truck is over here. What would change in the equation when I go through to do that? What's going to change? The signs. So now the signs are going to flip from using the top sign for each one to the bottom sign for each one, because now the motions are away from each other. So you're going to now hear a frequency. Billy would hear this to be 2,500 multiplied by 343, and now it's going to be the bottom sign, so it's minus 12. This is going to be the bottom sign, so that's positive 17. And now I have a number less than 1, and that frequency goes down. So 2722, it's going to go to a really low frequency after that. And you just compute what that is. 2298. Let's just call it roughly 3. Yeah, 2,700, 2,300 is fine. You notice a shift here of about delta F, approximately 400 hertz. So the difference in frequency that he's going to hear is about 400 hertz. Are you able to detect that? Yeah, you would be able to detect that. And so that Doppler shift is describing just how much that frequency shifts. In this case, it'd be more of a change in frequency from as they pass. Okay, I'm going to have you guys have you guys try the Billy on the bicycle and the ambulance and see if you can work through that equation. See if you can figure out how to write that, and then you can do the math to be able to get the answer. But get the equation written that needs to be solved. Go ahead and give that a go. Did you have a question there? You good? So if you're trying this problem from home, you should be trying to write that equation yourself. And then once you get the equation written, there's going to be some math to get to the answer. You have to choose the appropriate sign. So the detector is moving toward, we're going to use the positive sign up top. Source is moving toward, we've used the positive sign there. The thing we're looking for is the speed of the source, so then you have to go through algebraically to solve that, right? So there's all sorts of ways to do that, cross multiply, whatever, but get x by itself, go through and solve that. I'm going to write the solution up there to give you the number. Not going to talk you through it. You guys can work through that, see if you can get x. So that should be the answer. We'll get about 25.06, 25.1-ish or so. Anyone confirming? Okay. There's some algebraic work they have to be able to get through and do that. I didn't show all my steps, right? But you have to be able to rearrange and manipulate that, and so you get about the 25. You can always check that, plug that back into the base equation, and see if you get the right frequencies. I got one more. My last hour did not get this one solved because we needed to get into some lab work. I think what I'd like to do is I'd like to make sure we get this one solved. I want to get it on video. But there are a number of kids that need to still do that lab, correct? Because you were gone. How many people still need to do that? Instead of having you try to do that during academy or whatnot, I think what I'd like to do is the last 10 minutes I work with you closely. You can use that time to get through that lab. Everyone else, I'll give you some problems to work on for Doppler Shift. Okay, so if you have to do that lab with me today because you missed that lab day, you would have homework then for Doppler. Everyone else could have that other stuff. Can you guys try that one? Give it a shot. People in my first hour or fifth hour did not get this one solved, or they were asking for it, so I want to do this as well. See if you can set that up and go. You guys agree, if you're setting this one up, that you're trying to determine the speed of the sound wave. So you're looking for x there. I see why they were struggling a little bit with it, because you have x in both the numerator and the denominator, so the math becomes a little harder to go through and do. Hopefully you're in agreement that that's the way you'd set up that equation. Detector is not moving, the source is moving toward the spectators. So I'm getting the speed at which sound travels is about 350.5. Could be some rounding issues there, but about anyone confirming they're doing that? Okay, getting that speed. Now, if I'm looking for the temperature, then I'm going to go ahead and use let's see, the speed of the wave would be 331 plus 0.6 times the temperature, and that's equal to 350.5. So 19.5 is equal to 6.16. I'm getting T to be about 32.5 degrees Celsius. Okay? And so that would be how you might go through and determine how to use that Doppler shift to find that speed, and then also to use that temperature equation. Okay? All right. Any questions for me before we pack it up? All right. I'm going to go ahead and stop the video. If you're in 5th hour and you need to see that, temperature should have been about 32.5.